So on my previous lecture, I stopped talking about the phantoms and quasi-phantoms, and let me recall definition. So the definition triangulated an admissible triangulated subcategory L in the category of perfect complexes on X, where X is smooth and proper, is called quasi-phantom. If if the Hochschild homologies of L trivial and K0 of L is a finite group. So it's A and B. L is a phantom if K0 of L is trivial. So, and I also said that actually it's more reasonable to consider so-called strong or universal phantom. So this means that K motive of L is trivial. It implies that all K series of L, they are defined also trivial. And and what I say about quasi-phantoms, so at this moment we have a lot. So we have a lot of examples. And actually, I'm not sure that if I start to mention all last names, I will make a complete list. So, but just to say, so we have a lot of examples of quasi-phantoms, but all of them are actually coming from fake Delpezza surfaces. So this is a surfaces of general type. With condition that irregularity is equal 0 and geometric genius is equal 0, and for which Bloch conjecture holds. So there is a so-called Bloch conjecture that said that actually for any such fake Delpezza surfaces, for any surface of general type with Q and PG equals 0, actually if you consider the Joe group of the points of cycles, zero-dimensional cycles, that it's isomorphic to Z. And for many of them it's proved. So, and in this situation, actually, what we have a such surface S. We know, because Bloch conjecture holds, that K0 of S is actually isomorphic to the finitely generated abelian group of the form Z power E plus torsion in the Picard group, where E is the earlier characteristic of S, so it's equal to B2 plus 2, if you want. So it's C2, 12 minus C1, 2. It's a Noether equality. And so the people consider such surfaces. And finally, if you are lucky and if you have enough time and power to construct that some kind of exceptional collection of the length exactly E. So it's exceptional collection in the category of perfect complexes on S. So, and after that, you have to consider semi-orthogonal complement here. So you get a semi-orthogonal decomposition. And because this guy is K0 of this guy is actually exactly equal to this abelian group, then you will find, and because also the K0 is additive, so you will find the K0 of A is actually just a torsion in Picard group of S. And also Hochschild homologies are trivial. So everything over C actually here. So we have a lot of examples, but all examples of the such form.
You can't get these like these E's. They can't give sort of finite index, finite index subgroup of the ZE. Or how do you actually know it's ZE just because they're exceptional? It's because there's quadratic form or something, or.
Yeah, because it's generated the whole category. I mean that it's some kind of such thing. So it means that it's okay. It's some kind of it's every time it's easy to see in some sense. But I mean that it's every time such thing because it's a direct summand there. So I mean that because K0 is a additive invariant, so this means that K0 of this subcategory is a direct summand. Okay. So this means that it's a whole ZE. So, and what I want to say now, I didn't have time to say it on my previous lecture, that actually I'm not sure that in all examples, but exactly in the case that so I mean that we with Valer Alexeyev consider, and in many other cases, the situation is actually the following. So it looks like this category A is really, I mean, that simple, but actually it's not true. It's very complicated category. Why? Because I mean that if you consider the subcategory that is generated of this exceptional collection, so then you will find then in all examples that I exactly checked, that this category, it's actually formal as a category. So I mean that you can consider DG algebra of this exceptional collection. And actually this DG algebra is formal and doesn't have any kind of deformation. Doesn't have deformations. And if you consider some examples where so when you take some kind of such surface, for example, if you consider S, it's exactly that we consider with Valera, if S is, for example, Bournier surface. Never mind what is it, but I want to say that actually it has a four-dimensional family of moduli. And you see that actually this guy, I mean that the category that generated this exceptional collection, the same for all of them. So you cannot deform it. But we know also that the S in all these cases can be reconstructed from perf S. So it's some kind of theorem that says that if you have a variety for which the canonical class is ample or anti-canonical class is ample, then it can be reconstructed from the this category of perfect complexes on S. And it's exactly this case. I mean that in this case the canonical class is ample. It's in all these cases. So this means that actually this category, if we have this category, we can reconstruct S. But this category is the same for all of them. And if you will calculate it a little bit more, and you will find that actually the following. So if you consider the Hochschild cohomologies, so if you consider the Hochschild cohomologies of S and the Hochschild cohomologies of A, so you will find that actually there is a map here. And so the first, if let us put I here. So if I is equal 1, then all of them trivial. But for the second cohomologies, you will find that it's isomorphism. If I is equal 2, it is isomorphisms. So this means that all deformations of this category is exactly the all deformation of this category. Moreover, if I is equal 3, that it's monomorphism. So what I want to say here, I want to say that actually the all deformation of our category, of our surface S, and this of course implies the deformation of this category, all of them are exactly coming from the formation of this guy that is quasi-phantom. So it looks like very small guy, and maybe it's people can think that it's something very simple, but not. It's not simple thing. So I mean that it's a really complicated thing because it contains all deformations. So I mean that this guy see your surface in the 4-dimensional modular space. So this means it's very, I mean that rich object actually. It's a problem that, it's exactly the problem that we don't know how to construct such quasi-phantom in the internal terms. So for example, to find the DJ algebra, infinity algebra, that is exactly, so of course this guy has a classical generator. And of course, if you take this classical generator and take the infinity algebra of endomorphism of this GG algebra of endomorphism of this classical generator, you will construct such GG algebra that the perfect complexes over this GG algebra is exactly this category, and so on, so on. But I mean that it's really difficult at first to calculate it with GG algebra. It's not so difficult to find the generator, but it's really difficult to calculate it. So, and there's nobody at this moment produce any kind of abstract, I mean the GG algebra that give you a quasi-phantom, for example. I mean that it's a complicated thing. In spite of that, we don't see this guy, almost not see this guy on the level of additive invariance. And maybe just to, because we are actually every time think about something, some kind of mirror symmetry. I mean that it's of course it's very interesting. So it's a question how to construct to find a mirror symmetric object. So this means that to construct a Foucault type category that is quasi or phantom and of course it's reasonable to consider some kind of mirror to one of such surface. And I mean that there are, as I said, there are a lot of examples, but it seems that I don't know, of course, what is the best of them, but one of them looks like very good for considered mirror symmetric object. So I mean that if you consider the classical Godot surface, then it's given by equation of Fermat equation. And with the action of So we have a such Fermat equation, and after that the Godot surface is a quotient. So this is let us denote by S bar, for example, and our S is now the quotient of S bar by Z mod 5, where Z mod 5 acts as a just a on the coordinates just a 1 rho square, rho cube, where rho is the square root of fifth square root from unity. So it's such action. And now we can try to produce a mirror symmetric object. So it's a, as I understand that it's a Landau-Ginzburg model that is on A4 with a superpotential, maybe F is better here, of the same form actually. And with action of group of the form Z mod 5 plus Z mod 5, as I understand, that acts the following. So it's how it acts here. So it acts by multiplication of on rho A, rho power B, rho power C, rho power D, and where A plus B plus C plus D is should be divided on the 5, and it seems that also B plus 2C plus 3D is also should be divided by the 5. So it seems that if we consider such Landau-Ginzburg model, then we have one singularity at 0. It's isolated singularity, but the problem here that actually we have action of the group, of this group, and the problem that we cannot to deform our singularity, it seems, such that it will be some kind of Lefschetz vibration or something like this, because we have to keep in mind that action of this group, and we have do everything is equivariant. So I don't know how, but it seems that maybe it's possible to find the quasi-phantom here in the terms of Foucault category. So
why is this the mirror object of Godot surface?
It's some kind of general stuff. I mean that if you have some kind of superpotential of the form that it's a Fermat equation, then the mirror is also Fermat equation, and also only that you have to know what is kind of group acts actually. So I mean that it's general stuff is following. So if you don't have any kind of action here on this side, that on the mirror side you have a complete action. And after that, if you have some action here, then it's so I mean that adding some action here, it's killing some action on the mirror side. So that's all. You can some kind of dual group. So I mean that it's a.
So now we should compute Foucault side of category of this mirror.
Yeah, but the problem that there is an action of this group, so this means that I even don't know, is there any kind of definition, Paul, of the Foucault-Seidel category with action of group? I mean that how to...
There's a definition, it's not computable.
Uh-huh.
It's not necessary.
Uh-huh.
What if you divide by the group and resolve?
There's no reason why that should be the same.
It's a symplectic side. It's not algebraic geometry side. I mean that it's not a.
You send the Kähler form to a root of unity.
What you asking about symplectic form here or what? Yeah. No, I don't know actually. I mean that again. I'm sorry. So I just say what is a mirror, but how to say I cannot to say anything about the any kind of Foucault category of vanishing cycles here. So it's I don't know. I just show that actually in some cases it's in this case, or maybe in the case of Baville surfaces, it's also, I mean that it's not so difficult to say what is a mirror, but to calculate it, I don't know. So it was some part about the phantoms and quasi-phantoms, and now I want to talk about again the geometric realizations. And the gluing of categories. So what I mean the gluing here? So gluing means the following. Look, suppose that we have some kind of semi-orthogonal decomposition of a triangulated category in the form L1 and L2. So it's a semi-orthogonal. So this means that we don't have any kind of Holmes from this object from this category to an object of this category, and both of them generate the whole category. So all of them are admissible. So what I am what is a gluing actually? Gluing is an operation opposite to the semi-orthogonal decomposition. So suppose I have a L1 and L2, and I want to glue them, and such that to get a category T. Of course, everything, so it's possible, but of course everything should be done on the level of DG categories. So how it can be done, and what we need to glue. So of course it's not enough to have just only two categories. We have to have some kind of glue here. So, and what is a glue here? So I mean that it's a, let us consider the category that it's already the DG category of perfect complexes over one, say, one DG algebra A and another DG algebra B. So we have our categories, they are realized in such form. So, and now we want to glue them. To consider the gluing, we need to take just a bimodal. So S, it's just a bimodal over A and B. So here N and B are DG algebras. But everything is the same like for usual algebras. So no any kind of, I mean that formally it's absolutely the same. So how to construct gluing? Yeah.
Is this a new symbol like the pizza for 100 person?
It's a semi-orthogonal sum, okay? So I mean that it will be orthogonal, but it's a semi-orthogonal.
Pizza for 100 person.
Okay. Okay. So, how to construct such gluing? So let us consider the following DG algebra. So of course everything can be done without considering these algebras A and B in terms just the perfect complexes over A and perfect complexes over B. But the shortest way to say everything in the terms of algebras and bimodules over these algebras. So let us consider DG algebra C of the following form: A, B, 0, and S here. So it's it's also DG algebra. And let us consider the perfect, the category of perfect complexes over this algebra C. Then you will have that actually the perfect complexes, the triangulated category of perfect complexes over C has a semi-orthogonal decomposition exactly in such form. And moreover, any kind of semi-orthogonal decomposition can be obtained using such gluing. So let us consider example. So let us consider quiver. You remember that Kronecker quiver and vertices here. So one and arrows here, two vertices. And let us consider this category of perf over this algebra C. It has a semi-orthogonal decomposition, so it has two exceptional objects. So it has a semi-orthogonal composition in the form that it's just two exceptional objects, or perf K if you want. How to obtain gluing? So how to glue these two categories? We just need to consider the bimodal that is a vector space of dimension n. If you take this vector space of dimension n, and if you consider the algebra K, V, K, 0, we exactly obtain this quiver, algebra of this quiver, that's all. So this means that this perf of this C is just a gluing of perf K with itself using the bimodal V. Okay. So, and what we can say about the properties of gluing in terms of the pieces. So, as I said, I'm interested in such non-commutative varieties that are smooth and proper. And of course, it's naturally to ask when the gluing is smooth and proper. And it's a very simple statement that actually, so some kind of proposition. So a gluing perf A with perf B using S is smooth and proper if and only if both pieces are smooth and proper. And S is perfect as bimodal. So this means, yeah.
A and B are smooth and proper. S being perfect is the same thing as S being just proper.
Yeah. So, and now I mean that what we have now, so I mean that we have a big world of usual smooth and proper schemes, and we have some kind of admissible subcategories. So we have admissible subcategories in perf X, where X is smooth and proper, or a projective if you want, proper scheme, just usual scheme. L. So any such L is smooth and proper proper as non-commutative scheme. Yeah, we know it. So we have some kind of world of smooth and proper non-commutative scheme that actually admissible subcategories in the usual in the perfect complexes of usual scheme. For example, we have just the whole categories of these perfect complexes on a smooth and proper scheme. But also we have a gluing, so we can glue them. And we obtain new smooth and proper non-commutative schemes. My bad.
Is there, maybe it's not possible, but if I have just two varieties, x and y,
Yes.
is there a way to get one of these bimodules out of, say, something living in
Yeah.
the product? Or?
Yes, exactly. So it seems that on the first lecture I said this theorem of Toyn. It's exactly so, but I can repeat it. Yeah, I can repeat it. Yeah, that it's actually, it's a right question. So I mean that the perfect, so if we have x and y, then we can consider the perfect complexes on x cross y. And it's exactly the category of perfect bimodules over these two categories of perf x and perf y. So this means that the gluing, so if you have some kind of object E here, then we can glue perf x with perf y using E. And we obtain new non-commutative scheme that is actually smooth and proper. Okay? And if you consider general gluing, it's not any, so it cannot be realized. We consider this example. I mean that, again, I return back to Kronecker-Quiver. So it's a gluing of 2 points. But this DG category, it cannot be, I mean that for n not equal 0 and 2, as we discussed, it cannot be perfect complexes on a variety, on smooth projective variety. So sometimes, very, very seldom, we can obtain something that is also just a commutative scheme.
But it's given by some E in perf of point cross point?
Yes, V.
Oh,
It's
just a vector space.
yes, just a vector space V, as I said here. So.
With no structure.
Pardon?
Does it usually admit
So V is just a perfect complexes of a point. So it's just a complex concentrated in one degree 0. So I mean that's all.
what can you say about geometric realization of these gluings?
Yeah, it's exactly what I want to say. So I just mentioned here that actually, I mean that we have a large amount of non-commutative smooth projective schemes that are admissible subcategories. So in some sense, it's exactly such non-commutative schemes that have so in other words, in my terms, it's exactly the same that the non-commutative schemes perf E that have geometric realization. I mean that to be an admissible subcategory, it's exactly, I mean that's a tautology in some sense that it's exactly this category by, because it's admissible, it's exactly, it's a geometric realization. So it's a fully faithful functor to the perf x. That's all. But by construction. So it's exactly, and inverse also true. So I mean that suppose that you have a smooth and proper, and you have a geometric realization in the smooth and proper commutative scheme, then it's admissible. I said it on the previous lecture. So I mean that admissible subcategories, it's exactly non-commutative scheme that has a geometric realization. It's the same. But here we obtain a new amount of non-commutative smooth and proper scheme. And of course, it's reasonable to ask about geometric realization. It's exactly that I want to say here. And and there is a theorem. So let perf E1 and perf E2 be smooth, proper non-commutative schemes. That have geometric realization so say perf EI to the perf XI, and let S be a perfect bimodal, and in this situation it's necessary that its a gluing is a smooth and proper. Then the gluing of these two guys also has a geometric realization perf V for some smooth and proper V. So what I want to say that the gluing of geometric categories, so admissible categories, is I mean that it's operations then defined on the class of these geometric categories. So this
X1 plus X2 or something more complicated?
much more complicated, much more complicated. And the X1 cross X2 is not related actually to the gluing at all. Now, I mean that the general construction is pretty sophisticated, but there are more simple constructions when we glue, for example, just the points. So when we construct something like an exceptional collection or something like this, then it can be realized constructively and much simpler. So, and what kind of application, just to say some kind of corollaries here. So it's a immediately corollary that if so for any DG category,
Do you have a couple of examples of what V would be, like for autoequivalence kernels, etc.?
okay, maybe I say about exceptional collections, okay? So it's I mean that it's every time it's I mean that not direct and pretty complicated construction. So I mean that it's not one step or two. But for any DG category perf E with a full exceptional collection, so what this means with a full exceptional collection? So this means that actually this category, perf E, is just a gluing of perf K few times. Exactly how many exceptional objects we have. This is just a gluing with using some kind of perfect complexes here. Sorry. So again, the DG category with a full exceptional collection, it's a gluing of points. That's all. So, of course, because it's a particular case, it has a geometric realization. It has a geometric realization. But moreover, it can be realized as a subcategory of perf X, where X is a sequence of projective bundles. And this exceptional collection, let us denote it by L+1, exceptional collection here. And this exceptional collection is a part of the full exceptional collection. Can be extended to the full exceptional collection. Exceptional collection of perf X. So perf X, in this situation, perf X is a sequence of projective bundles. What this means? So this means that we start from point. After that projectivization, what kind of vector bundles we have? Just the vector spaces. So the first step is just we take some kind of projective space. After that, we take vector bundles E on Pn and take the projectivization of E over Pn. After that, we take E1, for example. E2 on this guy and take the projectivization of E2, and so on. So it's a sequence of projectivizations. So this means this variety has a full exceptional collection. Because projective space has a full exceptional collection, it's some kind of simple generalization of Bellingson theorem about the projective spaces. So it's a relative version of this Bellingson theorem. So it has a full exceptional collection, different kind of full exceptional collections. And I want to say that actually we can embed our, so we start from some abstract DG category with the exceptional collection. And after that, I want to say that there is a variety X that is actually rational, so it's a projectivization of vector bundles. And there is a realization such that this full exceptional here collection, here it can be actually realized in the form of line bundles up to shift. It's important here. It's absolutely general category with a full exceptional collection. So, I mean that if you have what is the general thing that if you have two exceptional objects, what kind? So here we have some kind of complex of vector spaces. So this means that you have just a gradient vector spaces of different homes. So it's yes, sure. Of course, yeah. It's just only that we have that it should be the bounded complex of vector spaces of finite dimension. Of course, it should be perfect. So this means that finite. So it should be finite as a total guy.
Is K any field?
Pardon?
K any field?
Yes, K any field.
Simple algebras?
Not here, because here is by definition I take.
Can it be done with simple algebras?
Yes. No, I mean that I just say another corollary. I mean that this. It's in some sense it's a corollary, but in some sense it's a separate theorem because I said more here. I said that it can be realized in such form. So it's not follows from this theorem, because this construction is pretty sophisticated, but it's another construction here. I mean that when you glue just an exceptional object, you can do it much more easy without any kind of difficult things. So and another also some kind of corollary, but it's not direct corollary. I mean that it's requires some proof. It's about the algebras. So I mean that what I want to say here, just to say the theorem, I just want to point out that if you consider finite dimensional algebra, and just usual algebra, not DG algebra, usual algebra, finite dimensional algebra, then you can consider the category of perfect complexes over A, and this category is a proper because it's a finite dimensional. And this category will be smooth if A has a finite global dimension. If and only if. Smooth if A has a finite global dimension. So this means that with any finite dimensional algebra of a finite global dimension, we have a smooth and proper, again, non-commutative scheme. Smooth and proper. And also it's reasonable to ask, is it has a geometric realization or not? And the theorem, yes. So it has a geometric realization if or if K is perfect as a field, or if A is actually, I mean that smooth. Look, I cheat you. So I said that it's a smooth when it has a finite global dimension. It's some kind of cheating. So when it has a finite global dimension, it's regular, but not smooth over a field that is not perfect, actually. So it's smooth over if it's a regular, so it has a finite global dimension, but also if it's if you consider quotient, I mean that semi-simple part of this, so quotient by the radical ideal, that it's a so-called separable semi-simple algebra. So never mind. I want to say that if it's smooth, then it has a geometric realization over any field, So it's exactly why it's smooth. I mean that it's a global dimension and this additional property. So should be smooth. It's also some kind of theorem that it's use Auslander construction. So the procedure is following. So we take the category of perf A, and after that we embed this category using some kind of Auslander construction to the category with that is has a full exceptional collection, but a little bit weak full exceptional collection. So it's a gluing of semi-simple simple algebras. Gluing not only field, but it can be Azumai algebras or something like this. So a field extension, so semi-simple algebras. So anyway, I just want to say that it also has a geometric realization. So it looks like every time, I mean that when we have some kind of non-commutative variety, so it's maybe some kind of conjecture. So any smooth and proper non-commutative scheme has a geometric realization. Pardon?
You take away smooth if you have a finite dimensional algebra that has infinite global dimension. Is there any?
Yes, it's not smooth, but also there is a. So I mean that in this situation there is a. Thank you that you asked. So so there is a geometric realization in the smooth and proper X. It also exists, but this category is not admissible. So realization exists, but it's not admissible if it's not smooth. Okay, but if it's smooth, it's admissible.
It's similar to a singular subhorizon.
Exactly that I wanted to say. Yeah. So exactly that I wanted to say here. So I want to say that about also non-commutative resolution. So what is non-commutative resolution? Non-commutative So a non-commutative resolution, so if you have some kind of non-commutative scheme, then non-commutative resolution, it's also some kind of realization, but not geometric, not necessarily geometric, perf, say D, for example, where this category is smooth. So it's a fully faithful embedding, fully faithful embedding to a smooth category. It's a non-commutative resolution. Why such name? Because if you consider just the usual resolution of singularities, so if you consider x and x tilde, that is a resolution, usual resolution of singularities, and let us denote by pi the Wies morphism, then you have a, of course, every time you have a inverse image functor from perf x, let's put perf x to the perf x tilde. And this category, if it's smooth, so this category is also smooth. Of course, it's not necessary that this functor is fully faithful. But if you have a rational singularities, so this means that direct image of OX tilde is exactly OX, this property, give you that in this case, it will be fully faithful. Moreover, it's proved by Kuznetsov and Lund that actually for any resolution, you can construct a non-commutative non-commutative resolution in this sense. So for it to construct it, you have to glue perf x bar with some other smooth varieties. So there is a such gluing that actually the natural functor from x to here, that it will be the fully faithful. So it will be a non-commutative resolution. So now, if we apply this theorem that I actually removed here, then we obtain that for any, so we obtain the theorem, so let X be a proper scheme. So it will be constructed by Kuznetsov and Lunds, of course, for fields of characteristic 0, because of course they used Hironaka theorem for resolution of singularities. And pardon? There are gluings, some kind of gluings. I didn't specify what is this smooth variety, but all of them smooth. Yes, there is a gluing. And so let X be a proper scheme, then there is a smooth and proper V and the fully faithful functor of perf X to the perf V. Why? Because by theorem of Kuznetsov and Lunds, there is a such fully faithful functor. But this category, by the theorem that I erased, this category can be embedded, has a geometric realization in the smooth and proper V. So, and if you compose them, you obtain this such kind of realization for any scheme, any proper scheme. You obtain such realization, such resolution, if you want, singularities for X. But of course, it's use resolution of singularities, the Hironaka theorem. So, and now I want to consider example. So, what kind of example I want to consider? It's just to say that there are some other questions about geometric realizations. So, for example, there is some kind of question that Bondel asked. So just consider the usual smooth projective variety. Is there any kind of geometric realization of a smooth projective variety in a Fano variety? So this means that is there any kind of geometric realization? So it's just both of them are usual varieties. So, but of course it implies for any admissible subcategory as well. So suppose we have a smooth projective variety. Is there any kind of geometric realization? So this means that fully faithful functor to perf V, where V is a Fano.
Let me just have to ask a question. It's wrong. If I just have a closed subvariety,
No.
then that doesn't.
No.
There are more or less.
No. No, it should be the full admissible subcategory here. It's, I mean that, for example, if you consider curve, if it's not a P1, and if you consider this category for curve, it doesn't have any kind of admissible subcategories. Okay? Except trivial, I mean that's 0 and itself. So it's really difficult to find any kind of admissible subcategory in the category. But let us consider example that is it's not maybe difficult, but it's definitely related to mirror symmetry. And let us consider, and also it has a lot of interesting properties that I want to show.
Do you never compare the dimensions of the categorical resolution?
No, I didn't ask it here. So if you want, you can ask, but it's additional thing. So I mean that it's something more stronger to ask that it's has the same dimension or something like this. So let us consider the following quiver. So it has 3 vertices, 1, 2, 3, and 2 arrows here, 2 arrows here, so denoted alpha 1, alpha 2, beta 1, beta 2, and we have a relation here that so beta j alpha I is equal 0 if j not equal I. So this means that from this, so if you consider compositions, then we have 2 arrows from this, the first vertices to the third vertices. Let us denote by gamma 1 and gamma 2. So gamma 1, it's just a composition of alpha 1 and beta 1, and gamma 2, it's a composition of beta 2, alpha 2. Let us consider such quiver. So, and let us consider the category of perfect complexes over this quiver. So why it's interesting? I mean that why this category is interesting? Because actually it has a mirror symmetric category. What is mirror symmetry here? So mirror symmetry here, it's a Landau-Ginzburg model where the total space Y is just the elliptic curve without flex. So it looks like and we can write it as, for example, in affine coordinates, something like so y squared is equal 4x cubed minus g2x minus g3 in Weierstrass form. Then the superpotential here, so it's a map to a affine line, it's just a x. So I want to say that this quiver is exactly in some sense that mirror to this Foucault-Seidel category of this Landau-Ginzburg model. But why this category is interesting? Because actually it has the following interesting property. So of course we have a full exceptional collection here, and we can consider just the projective modules here. And it forms a full exceptional collection with exactly Holmes as this quiver. And but also we have another exceptional object here. Let us denote it by Ti. It's just such representation that of this quiver that it's a one-dimensional vector space, V1, V2, V3, one-dimensional vector space. And action, so I consider the right module, so this means that it's a representation of the inverse quiver, opposite quiver. So, and it's a, so this is Vi, dimension of Vi is 1. So, and the Ti here, so Vj. And Ti when the alpha, so beta I and alpha I acts as isomorphisms, and other guys acts as 0. So we can consider such representation, and it can be proved that Ti, so we have two such representations. So if T1 when B1 and alpha 1 acts as an isomorphism, and B2 and alpha 2 acts as 0 and opposite T2. So and Ti exceptional objects. And we can consider decomposition of our category in 2 forms. So the first form is a T1, it's an exceptional object, and the semi-orthogonal complement here, some subcategory L1. And T2 and some subcategory L2 here. This example is interesting because actually these subcategories do not have an exceptional object at all. So look, this category has a full exceptional collection, but these 2 exceptional objects cannot be extended to a full exceptional collection. So, and we have 2 categories, L2 and L1.
Is T1 and T2 Calabi-Yau by any chance?
T1 and T2 just exceptional object.
Oh, sorry, is L1 and L2 Calabi-Yau?
No, they're not Calabi-Yau, right? A Calabi-Yau category. But what I want to say that actually all this stuff can be included in as a picture. So we can consider variety curve C and consider the curve C, where C it's just a cubic with one double point. So let us consider such curve. What I want to say here, I want to say that actually there is a following diagram. So we have a curve QI here. We have two subcategories L2 and L1 that are full subcategories here. So these give us the two non-commutative smooth proper schemes. And we have a curve C here. It's not this category is not smooth because C is not smooth, so it has an ordinary double point. But we have a full embedding here and here, such that the composition it's a full embedding here. So this means that these two guys are the non-commutative resolution of these perfect complexes on this curve. This guy is also non-commutative resolution, but not small, not the smallest. So these two guys are the small non-commutative, smallest non-commutative resolution. And moreover, I mean that relation between them can be, it's like the picture about flop. So it can be called one-dimensional flop. So relation between these two categories, it's one-dimensional flop. So I mean that it's exactly the picture that looks here, that if you have a three-dimensional variety with -2 curve, and we have a so-called flop, just a usual Atiyah flop here, and you can contract this curve here, so you get something really singular. And you have the same picture here, and the flop here. But it's three-dimensional. But this guy is a one-dimensional flop here. And moreover, I mean that the mirror picture, as I said, for this guy.
Aren't there two ways to construct the functor?
Pardon?
In the three-dimensional picture, there are two ways to construct the functor associated to a flop.
Well, I was going to say, in that case, the receipts are actually the same, aren't they?
Yeah, they're saying.
It's a birational transformation. It's not a functor, so it's just a relation between them. It's a birational transformation. It's not a functor at all. I just say that they are related to. It's not a functor. It's not a direct arrow. So I mean that it's just
But I thought this was a situation where
some kind of relation.
were actually equal, two different hearts in the same.
Yeah, they are equivalent, these categories. And here, these categories, of course, equivalent. So I mean that there is an abstract equivalence between them.
Why, of course, equivalent, sorry? Oh, because there's an.
Because it's easy. So I describe now everything more precisely. I just want to say the mirror for this guy, it's elliptic curve without flex with a superpotential double V is equal X like there. But mirror for this guy, so this is a C, and C is just a elliptic, I mean that not a cubic with a double point. So the mirror to this guy, it's just a elliptic curve without point and without any kind of superpotential. So no superpotential here. And also, as I learned from discussion with Mohammed and Denis, so it can be defined the mirrors like Fukaya type categories. That are related to these L2 and L1. Of course, they should be equivalent. So some kind of Fukaya L2 and Fukaya L1 here should be. some Foucault category. I just want to say how they, how these functors looks like. So for example, how to describe this category in terms of DG algebra. It's easy. So I mean that you can consider the generator that is a structure sheaf of C. And for example, structure sheaf twisted by point. That point should be, of course, not singular, but smooth point. And the DG algebra of this generator will be the following. So we have two vertices. We have one morphism to this direction. It has a degree 0. One morphism in this direction, degree 1. And has a composition of these morphisms. So we have a morphism of degree 1 here. And that's all. So I mean that this is exactly the complete DG algebra that describe this category. So, and to describe these two categories, L2 and L1, in terms of DG algebras, we have to consider the following quiver. So we have to consider the quiver that it has a DG quiver. It has two arrows of degree 0. So let us denote it by, for example, X and Z. I say Y. And Y, it's a degree 1 here. And we have just a composition of the form XY, YZ, and XYZ. So this means that if it's opposite, it's 0. So it means that some kind of lexicographic order here. So we have so this is a degree 1. This is a degree 0. And of course we have some such arrows degree 1 also here. That is just this composition. And these guys are exactly X, Y, and this is a YZ here. So this is DG category that describes these L1 and L2. And this category, you have a description. And it's easy also to describe the embedding here. So for example, what is embedding of this category to the big one category that has an exceptional collection P1, P2, and P3. So this is exactly one object, a structure sheaf of C, go to the complex that is a morphism of P1 to P3. And this morphism is not degenerated, so it's some kind of sum of alpha 1 plus alpha 2. And this object go to the P2, to the complex P2 to P3, beta 1 plus beta 2. So, and it's give you the precise.
I'm about to threaten you with giving you part 4.
No. I stop here. So I will stop here. So I just wanted to ask maybe Denis just 1 minute just to say what is actually Foucault categories here. He described me that it's some kind of Foucault categories with stops, so-called. So, and it seems that it's exactly the complete mirror picture can be described here. So I will stop here. So.